So thank you very much for the introduction. I would like to warmly thank you for the invitation. I'm very honored to give a talk for the Jubilee of Alexander Yuryevich. For me, as a student, it was a big name in stochastic analysis. And then I had the pleasure to meet him and to interact with him. It's always a great pleasure. I must as well say that he did a lot of efforts to show me very nice places in Moscow, and this is very highly appreciated as well. So thank you very much, Alexander. The talk today will be about convergence rates for the Euler-Maruyama scheme applied to diffusion processes with singular drift in the Lebesgue setting. And this is a joint work with Benjamin Jourdain from the CERMIX in France. So we consider a stochastic differential equation of the following form with additive noise and drift, which belongs to a Lebesgue space, a time space Lebesgue space, in LQL rho norm, where Q refers to the time variable and rho to the space variable, under the so-called well-known Krylov and Ruckner condition, which means that it's d over rho plus 2 over q strictly lower than 1. And I recall that the associated norm writes as follows. We integrate the space variable in rho and the time variable in q. Okay, so it is well known now that since the seminal paper of Krylov and Ruckner, which was indeed based on the initial ideas about strong uniqueness going back to Zvonkhin and Alexander Yuryevich, they got strong well-posedness of the equation under this condition. And to be complete, let us as well mention that as far as strong uniqueness, strong well-posedness is concerned, the critical case has recently been addressed by Krylov. I think he would talk about this later on this afternoon. And in the homogeneous case, in the first paper, and by Ruckner and Zhao for the inhomogeneous case. So to give some hints, the weak existence to he is obtained through Girsanov arguments and Hashminsky's lemma to derive exponential integrability. Okay, indeed, if you simply get interested in estimating for a drift in LQ, L rho, this kind of moments appearing in equation 1.1, then you have got some regularizing effect. And to get deeper into the insight of the condition, how does this work if we consider a generic function in LQ prime, L rho prime, with a condition which is relaxed with respect to the former Krylov and Ruckner condition? There's a 1 instead of a 2. There's a 2 instead of a 1. Then the underlying idea is to proceed using a Hölder type inequality, making the L rho prime special norm appear. So of course, this induces a time singularity with respect to the Gaussian density, which has precisely S minus over T rho prime. So we go back to the spatial exponent, and integrating in time, we make the norm appear, and we've got exactly this condition for the time integral for conjugate exponents, and this precisely lead in order to exhibit some regularizing effect in time, or for this quantity to be finite, we naturally find that the previously stated condition appears, namely 2 over rho prime plus d over rho prime plus 2 over q prime strictly lower than 2. And of course, if we have in mind a kind of Girsanov argument, then we might go to the square of that, and this precisely lead to the so-called Krylov and Ruckner condition. So this is the way we can get weak uniqueness through Girsanov, and then you have to do some more sophisticated tricks to get strong uniqueness, which are based on harmonic analysis estimates for the case of Krylov and Ruckner. Okay, so as equations of this following type appear, for instance, in statistical mechanics. I mean, equations involving a singular drift. We can refer to the works by Albeverio and his co-author. We can, for instance, mention the Biot-Savart type kernel of the form x divided by x over t. in terms of singularity, which are also the kernels appearing for parabolic elliptic heterozygal models, which are almost accessible in dimension 2, namely for x divided by x 2 minus epsilon belongs to the indicated class. Okay, and it's the first step toward even rougher drifts, because we can mention, for instance, connection with the stochastic, with the Navier-Stokes equation. If we consider a Leray solution, which typically induces to consider the drift as the solution of the Navier-Stokes equation. A Leray solution lives in L infinity L2 intersected with L2 H1 in D equal to 3. But of course, there is an additional information with respect to the generic cases I've introduced before, is the fact that the divergence is free. And of course, the Krylov and Röpner condition is violated, but we have some additional structure. Okay, the gradient is in L2, L2, and the divergence is 0. So I can mention the existence established by Zhang and Zhao in this context for the stochastic equation, but still without uniqueness. So these are just points in order to illustrate that it's important for approximating the diffusion processes related to such concrete physical models to have a good understanding already of the LQL rho setting. We can also mention that the Krylov-Röpner condition is somehow very similar to the serine condition appearing in the Navier-Stokes community. Okay. So now for the approximation, what are we going to do? Because we have a singular drift. And of course, we want to consider an approximating scheme. We give ourselves a time step, h, which is t over n. We consider what we will call a regularity index coming from the Krylov and Röpner condition, which is alpha over 2, corresponding to 1/2 minus 1 over q plus d over 2 rho. It's 1/2 the distance to the singularity in the Krylov and Röpner condition. And we consider two possible drifts, namely, the drift has to be cut off because it is potentially unbounded since it belongs to an L rho space in time. And we have to cut it off. And we chose two possible ways to cut it off. A cutoff associated with the so-called Krylov-Röpner regularity index, so making precisely the condition appearing in the cutoff, and the one which is more Brownian-related in the sense that it corresponds to the drift introduced in 2.2, where we cut off at the level h minus 1/2. So this is done in order that the corresponding approximation scheme does not prevail with respect to the Brownian increment. So again, since we also do not have any smoothness in time, we need to introduce some randomness as well to consider the inhomogeneity of the drift, considering independent sequences UK, which are uniformly distributed on tk plus 1. Okay, so with those definitions, we can define the scheme associated with the SDE. Namely, it's a usual Euler scheme for the random increment, and we consider BH, which is the singularity related scheme taken at UK being a uniform random variable. We again involve as in the usual Euler scheme, the previous value at of the scheme at the time. We can consider as well, of course, a time continuous interpolation, as this is usually done in stochastic numerical analysis. And the same extension do extend when we consider the scale-related scheme involving bar BH instead of BH. So these are the two schemes we are going to consider. And again, I do insist that for both schemes, the cutoff gives that for each time step, the drift remains negligible with respect to the Brownian increment. right? So we can expand that, we can express the density of the scheme on some time step in the following way, okay? And indeed, if noting that the drift enters in the Gaussian transition, what we can say, as it's indicated in 2.3, is that the density of the scheme still remains negligible and somehow comparable to a driftless Gaussian density. And this truly means that locally the drift is negligible with respect to the Brownian increment, okay? So now what can be said? Of course, to go further, we need some density estimates for the scheme. And the issue is to derive non-exploding Gaussian bounds for such a density. And the point to derive such bounds consists in rewriting the density of the scheme in a Duhamel type manner. This is done in equation dH, where we write that gamma h tk x t y of the scheme can be seen as a Gaussian density with variance 1 for the corresponding points and time scales, minus a perturbative term, which precisely comes from the Duhamel or parametrics expansion, if you want, which makes, again, the law of the scheme appear, since we have an expectation, and the gradient of an underlying Gaussian variable. So this is what needs to be investigated to derive that actually the density itself enjoys a Gaussian upper bound. It would as well enjoy the similar Gaussian lower bound in terms of driftless Gaussian random variable. And furthermore, what will be specifically needed for the analysis of the convergence is that we are able to give some other estimates with respect to the forward variable of the density of the scheme. This is what is summed up in equation HHKH, and namely, we are able to derive some alpha Hölder continuity up to the threshold to the singularity and the distance of the parameters to the critical value 1 in the Krylov and Rückner condition. So these are the key estimates we will need for the analysis. So now we have the density of the scheme, some related estimates, and through limit, so of course, we have, sorry, I was a bit fast with respect to what I wanted to say. Of course, this is the so-called parabolic scaling. The regularity on the forward variable transfers to the forward time variable with square root over 2. And this is the point of estimates 2.4. And of course, as well, I stated the estimates for the singularity-related scheme, and these estimates remain valid if we replace the cutoff by the natural one associated with the scaling in h minus 1/2, where h 1/2, again, is the typical order of the Brownian increment on one time step. So what I wanted to say is that since our Gaussian estimates for the scheme are independent on the discretization parameter, this passes to the limit and allows to derive somehow similar estimates on the density of the diffusion itself. So it means that the diffusion, the initial diffusion for which Krylov and Rückner first established strong well-posedness also enjoys Gaussian estimates. So from above and below, so there should not be absolute values for the density estimates, since it's not negative, and it as well satisfies the corresponding lower bound. We have the same spatial smoothness, okay, and okay, there it is. Sorry, there is a typo as well here.
Sorry, what is S in the second inequality?
It's
what is S? Left-hand side, there's no S.
There is no S. I'm terribly sorry. It's a typo. It should have been S actually. Instead of T, one T should have been S. No. Yes, one T should have been, no, it should have been S. Sorry, instead of 0, it should have been S. Instead
0?
Of 0, yes.
What is? It's supposed to be 0. Okay.
replace 0 by S and the estimate is correct. I do apologize. It's inhomogeneity, but thank you for checking. Thanks again. And do not hesitate if you have additional comments. I hope there will not be additional typos. Okay, so passing to the limit, we find again that we have the similar Duhamel type representation for the density of the diffusion. And even more general estimates for this density. In some sense, we have as well the gradient with respect to the backward variable, the Hölder moduli of the gradient. And I would like to say that the technique we use to derive those estimates is similar to the one that we introduced in a work with Antonel Lopesce and Xisheng Zhang. Okay. So in some sense, those bounds specify the Krylov bounds in the sense that, of course, the so-called Krylov estimate gives you that the expectation of the integral of Fs xs integrates that way. Of course, this is compatible with the Gaussian bound. We exactly say that we have a Gaussian bound for the density. Again, the absolute value should disappear. Sorry for that. So the main theorem is the following. Is about the convergence rate for the Euler-Maruyama approximation with these singular drifts. So again, alpha is the distance to the singularity. And what we say that there actually, for any constant c, there exists another constant, such that for any h, we have that the distance between the densities of the scheme and the density of the diffusion is controlled by a constant h to the rate alpha over 2 multiplied by a density, a Gaussian density, plus an additional logarithmic factor for the threshold-related cutoff in the one-dimensional case. Okay, so this is satisfactory from the from some point of view because we have a very precise description of the error. It is not that satisfactory from other point of views because, of course, when we are close to the threshold, to the criticality, the error rate almost vanishes. Okay, but this is a first step in the study of the weak error for a singular drift. So this is what can be said. So now just some ideas about the proof. So let's X be an abstract diffusion with additive noise and XH its Euler scheme. I would like to introduce what are the ideas beyond. Of course, we all know that there is an underlying PDE, the so-called Feynman-Katz PDE beneath, which plays a very fundamental role in the error analysis in the sense that if we denote by EXT phi H the error associated with some function phi, okay, between the Euler scheme and the abstract diffusion, the point is to say, well, I make the increments of the PD appear. I use the PD in order to make a telescopic sum appear. I use Ito formula, okay, right? The idea, of course, is to kill with the PDE the first order terms and to investigate the other ones, okay? And what can be said? So we end up with this expression. If B and U are smooth, then we can iterate this approach and find that the global error has order H. So this was the seminal idea from Talley and Tubar, and there is a huge related literature. When the coefficients are less smooth, but still a bit smooth, we can refer to the usual parabolic theory by Friedman or Ladizhenskaya, Solonikov, Uraltseva, which give that there is a parabolic bootstrap, that U is smooth, and in some sense, so U is smooth so that the gradient above is well defined. And since the coefficients are smooth, the B here is smooth, we can use some other smoothness to derive that we are H gamma over 2 smooth. So this was, for instance, introduced in the paper by Mikulevicius and Platon. Okay, right. It was used as well in the paper with Konakov and by Frika for density. So this is in some sense rather sharp when there is truly a diffusion coefficient. But if there is no diffusion coefficient, but the drift is not smooth, this cannot hold anymore. So what is the ID? What is the ID? And this is what I would like to discuss now. There's no more smoothness on the coefficients. So the point is to shift the analysis and to derive some smoothness, giving the error rate from the law. So go to the law, exploit the regularity of the law when there are no more smoothness of the coefficients. So recalling that in our current setting, the error writes in the following way. Okay, so we say we can introduce a pivot because we have BSXSH nabla USXSH. So, okay, this involves the law of the scheme at time S. So introducing a pivot term, which is the one in gradient US, in gradient U capital U S over H X tau SH, which is tau SH is the time step associated with the variable S. Then we make the difference of the law appear. The difference, the sensitivity in time of the law of the Euler scheme. Of course, we have as well the sensitivity of the drift, and we again have some sensitivity, some smoothness of the underlying PD. So, but here you see somehow you do not have the explicit smoothness of the coefficient. So we shifted all the increments on the law on which we are able to establish some smoothness. So this is really the underlying idea. And going now back, we wrote things for a formal phi, an abstract phi. If we can take for formally a direct mass at point y, we go to the density, so this can be possible. And we make, this is not the way we analyze the error, but it's the easiest way to understand the ideas beneath. We make three kinds of terms appear. Here, the green one is the one associated with the sensitivity of the gradient of the diffusion. So this is why, in some sense, the estimates on the density itself are very important. The red one is the critical one, which precisely make the time sensitivity of the Euler scheme appear. Okay, and the blue one is a term associated with the truncation of the drift. Okay. So these ideas were already in some sense present in the L infinity setting by and used by Oumema, Bencheikh, and Benjamin Jourdain, but we extended it with Benjamin Jourdain to the whole LQ, L rho setting to derive convergence. Okay, so I don't know if I have some time to give some ideas about the estimates. Sorry? It's time is up. Okay, time is up. So this was a slide associated with how one can derive the heat kernel estimates following the approach we developed with Shisheng Zhang and Antonello Pesce. Okay. Well, just to conclude, I would say that, of course, the approach could extend to the multiplicative node. It would not be a difficulty if we have assumed, for instance, that sigma is uniformly elliptic bounded on Lipschitz, the result should remain the same. We could as well handle other type of noises, for instance, isotropic gamma stable processes. And of course, some open questions concern the extension to more singular drift, like the critical case, or a distributional drift. I would like as well to indicate that some related error estimates have been obtained by Koale and Cheng Ling for the strong error, and their arguments are namely pathwise. They strongly exploit stochastic Sewing arguments, and they reach in the Krylov and Ruckner setting additive an error rate which is 1/2 up to a logarithmic factor, which is the one which is expected. Of course, we match going to infinity, but we do not match when we go to criticality. So I understand the difference technically, but in order to improve the convergence rate I presented, which are again on the density, so it's a different kind of error rate because it's in some sense, more precise if you are interested in a very specific function of the scheme of the diffusion. And in that sense, we need to improve the density estimate, the smoothness in time or in the final variable, and this requires additional techniques which are used when dealing with singular drift. So I thank you very much for your attention and again for the opportunity to give this talk.